All right, everybody, how we doing today? Doing good? All right, so today's our little study session. It's not going to be too long, but I just want to answer any questions. So, first of all, how's Dr. Morris's class? Not too bad. I never asked a question like, because I know he has like videos. Like it's like what is it? It's like, is it pre-recorded videos or a live lecture, right?
Well, he does both, where he has the pre-recorded videos on like
Panopto?
Panopto, and then in class that's when it's like live and we like ask.
Oh, so literally, your homework is to like just watch the Panopto before coming into class.
Mm-hmm. It's like a flip classroom.
Okay, not too bad. Okay, that's not that bad. I like that. So it's not too bad. You guys know, you guys are understanding what's it call it? What are signals, right? Right. You've seen so many signals, right? Like what's this one right here? I don't know. I'm just gonna draw some signals. Like is it sine?
Yeah.
Sine t or something like that, right there. Same thing, cosine or what's a what do you call it? What do you call it? Impulse. Oh yeah, you guys know those things right here. So if I were to draw this is t, right? The Dirac delta, Dirac, right? What's that? If I had to use a different color, I'll just grab my magic markers. Let's use red. If I did the following, right, it goes up to infinity, right? Because it's bounded between, what do you call it? It's equal to, what do you call it? I'm trying to remember this one, y'all. Give me a second. Because it goes to infinity, but the actual bounds are super tiny. Is that correct? Yeah, it's literally it's like it's a square, and then it only exists from, what do you call it? 0 to, what do you call it? T. What do you call it? I'm gonna do something funny. 0 something. I don't know. Point is, it's infinitesimally tall. It like goes to infinity, right?
Yeah.
But it's super skinny. So like this increment right here is like really small. So it's like very tiny. Yeah. So there's an epsilon. But then when you integrate this, right? So you just do an integral. What do you get when you integrate the delta function? You get the 1, right? So that's the u of t, right? So then you get this right here. It's 1, and then here's t, and here's 0, right? Not too bad. Easy stuff. Do you actually remember this? It's going to be on the exam. Actually, better yet, how about the reverse? Huh? Made? Let's see. No. Just kidding. No, it's already there. So Joanna is going to be the one proctoring the exam. She's in the back, so make her happy. I'm not saying to give her treats or anything or food. Huh? Yeah, so yes, do not be late. Let's put this in the video. What time is it going to be? 1 o'clock? 1 p.m.? Huh? 1 o'clock to 2:15 p.m. in the CHB. Is that what it's called?
Yeah, they're
Same classroom you guys have been attending Dr. Morris's hours, correct? So, okay, now it's on recording, so now everyone knows. Anyways, you guys remember, okay, going from here to here, right? How about going backwards? What do I do? So if I did like a, what do you call it, d over dt, derivative, right? Right? What happens? Yeah, you just get it back. Not too bad, right? So when we're doing impulse responses and step responses and the other way around, right? Does that make sense? Now, you know what? This is a great lesson because honestly, this is literally one of your problems. Did David have the exams? I don't know. You tell me. How about for, what do you call it, discrete time? Right? So we have our dn, right? It's the Kronecker delta, right? Does he call it Kronecker delta? No? Okay, man, that's a Dr. Stuber thing then, unless you remember. Yeah, Dr. Stuber is super theoretical. He's like the axially kind of person. So like, I'm just trying to graduate, y'all. So anyway, it's a delta function or D, or some people call it D, delta. Don't call it delay. It's not a delay. Okay. So what's this going to look like in n time?
0 to
1, right? And that's really easy to understand. So it's going to equal 1 at n is equal to 0, and then it's going to be 0 elsewise, right? So, okay. What if I do an integral? What's the similarity, or what's summation? Or yeah, I was going to say, what's the equivalent of an integral? It's a summation, right? If I do the summation of this right here, if I add it all the time, what do I get? I get the, I like switching colors like this, right? You get the unit step, right? How about the other way around?
get this subtract 2 steps.
How do I do a funny difference, or what do you call it, derivative, or a change? I don't think you guys, did he tell you about what this could also equal? Okay, hear me out. You see this pulse, right?
Yeah.
How do I create this pulse from a unit step? Remember? U of n minus u of n minus 1, right? And then you just get that function back again, right? 1. This is 0, 0, n, this is 0, 1, 2. Is that cool with everybody? Can everyone do a step response of a discrete time system, a step response of an analog system, right? What about the impulse response? Well, this one's the tricky one, of a discrete time system. And then we can do the, what's his name? Impulse response of, what do you call it? Well, the derivative of this, right? Okay, well, let's put some terms, because I'm seeing some yawns and like, whoa, what the heck's going on? Can everyone agree that this right here looks like a step, right? So this is a step, right? It just, you go into the lab, you press VDD from, like, you turn it on, like flick the switch, right? Now it's constantly on. And then you see what happens. It wiggles and sets, right? This is our impulse response, right? And then there's the question, can we build this? Yeah, there was a student, Dr. Baker, if you guys remember, who was like, I wonder if we can build this. I'm like, can't build it in analog. So anyways, the communications people think they can, but this right here is an impulse. Okay? So don't forget that. That's going to be on the exam. Let me just check. Yes. So if I were to do the following. Huh? No, just the practice. Didn't he go over the video? Yeah, what did he go over in that video? System properties. Did he go over Fourier series, LTI systems, right? Block diagrams. Did you talk about step responses? Am I surprising you? No, really. It's probably the same copy paste exam. I'm just giving you guys big hints. So please review these notes, okay? So if I were to do the following, let me just look at this practice exam right here. Let me see. If he were to give you the following, let me see. See, I'm gonna come up with something right here. So if we define a step response, right? And I'm gonna do, like, I don't know. Let's do 1/4, right? U of n, right? This right here is a system right here, right? It's a system, correct? This is S, right? For step, right? Make sense with everybody? What's this right here? It's a step, right? So what is this right here? It's a response to the step. Make sense? So if I were to give you the signal, I don't know, let me just come up with it. X, let's see, let me not do this. Let me see. X of n, let's see, X of n is equal to U of n minus 1. All right? Is that cool with everybody? If I were to turn, this is your input, right? And this is your response, right? Does that make sense? If I were to turn this switch on at, okay, actually, let me define something even deeper, okay? This step response assumes X of n is equal to U of n. Right? Right? Assumes that. So if this is my input, what is my new output? With this being my input and this is my response. So this is my response, right? And this is my output, right? If this is my input, right? U of n, the unit step, right? What's my output? Y of n is equal to S of n. Does that make sense? Let me see. Is this making sense? Because this goes to, and it turns off. That's good. That's what we want. You see, I'm trying to see how this, because hear me out, y'all. If n goes to infinity, right? This is going to decay, correct? Is that good with everybody? It just goes, like, I'm going to draw it right here. Here's S of n, okay? I'm going to flick it on like this. Well, it's going to do this at 1, right? And then 1 to the 4th power, or 1 is just 0.25, right? There we go, 4th right here, right? And then it's just going to decay, right? Does that make sense? That's a step response, right? So, if this is my input, what's the step response due to this input? N minus 1, right? What about this? Congratulations, you passed. Was this class hard?
Extremely.
Really?
Yeah, this is not taking it for the second time.
It's okay. Anyways, what if I were to tell you, you know the step response, right? But what's the impulse? So this is page 2. Okay. Oh God, I'm so sore. If anyone's noticed, I've been going to the gym. Yep. Goal is to become the buff EE and be like, yep, this right here powers op amps.
Electrical engineering?
Huh?
The Sam Sulek of electrical engineering? You don't know who he is?
No.
Really? You don't know who Sam Sulek is?
Sam Sulek?
Yeah, he's a mechanical engineering student. He's really buff, like really strong. He's like Hercules.
Anyways, S of n and U of n, okay? Remember that thing I talked about at the beginning? What was it? This right here, right? What's the impulse response? This is one input, right? This is another input, right? So let's just define it. If I were to make my, what do you call it? Impulse response, H of n, right? Is equal to S of n minus S of n minus 1, correct? That's my impulse response. And then you guys know the relative thing, right? It's like, I see, D of n is equal to U of n minus U of n minus 1. What's the impulse response? Just shift it. Are there any questions about that? The exam says yes. Or I don't know. No, I don't know. Shifting. Shifting property, was that one of the properties you learned? For linear time and time invariant systems? Does that make sense? So you guys can do, what do you call it? Step responses. What about, let me see. Let me look at this other part right here that I have. Boo-ha-ha. Let's flip it on you. So let's say if I do the following. analog, right? Correct? If I do the following, e to the minus 2t, right? U of t, right? What's the first step? This is a step response, correct? Or this is the step or this is a step, right? Step response. Exclamation mark, right? What do we have in that step response? Step, correct? So then if I gave you the input, let me see what's a good input. Literally, I don't know. I'm just going to do the same example. X of t is equal to u of t minus 1. What's y of t? Just shift it. This right here assumes, I'm going to write in a green marker again. Right? Not too hard, right? So all you do is just shift. Okay? Shift. Cool? How about the impulse response? How do I find that? Remember that thing I talked about in the beginning? Someone's going to forget about it. Derivative. So all I do to get the impulse response from the step response is boom. You might have to know the product rule for this guy right here. Any questions? Everyone going to ace that problem? Anyways, what are other things he talked about? This is page 3. Did he talk about LTI systems, the properties, what's memory, or actually, let me talk about block diagrams. Are we masters at doing block diagrams? Should I go over it?
Yeah.
Okay, let's see what I got cooking for you. There we go. Let's see from the practice exams. If I were to give you a general equation, okay, y of n, what do you call it, is equal to x of, x of n, what do you call it, plus, I don't know, x of n minus 1 plus y of n minus 1, right? If I gave you that equation, okay, just think about this for a second. What's the first thing I should think about?
You were having a process.
Huh? Does he have ways of solving for those equations? For df2 and df1? Difference equations? It's the same equation, right? Yeah, there's that too. But just do this for general practicing. Remember the delays, correct? Right? So this right here is, there's no delay, right? And that corresponds to the B0 term, right? Remember that? What about this guy right here? B1, right? What's this? Actually, what's B0 equal to? 1, easy. What about this one? 1. What about this one? So this is right here is the A1 term, right? But there's a funny surprise. Treat this as the negative A1 term is equal to 1. Does that make sense? The negative, okay, if this was a company block, if this was an op amp, this is an op amp right here, this is an op amp, this is another op amp, okay? I actually don't know how Dr. Morris is teaching it, but this is the way I've been taught. This is a puzzle piece, okay? Negative A1 is equal to 1, right? Everyone understanding what I'm saying with that? So treat this as puzzles. I'm gonna use this green marker. This is my favorite color. So df1, right? It's the first thing we do. X of n, right? And then let me just draw this dot right here. How do you guys draw it? I don't know. I draw it like this. D. And then let's build our part. Okay, we're gonna build a part from DigiKey. Okay, here's my green box, right? B0, right? Is that correct? I'm going to put my other puzzle piece right here, B1, right? And then I'm just going to eyeball it. I'm going to put right here minus A1. Are you guys seeing the puzzles? Right? So now all we got to do is just draw your arrows, make it nice. Grader's going to be happy. I don't think she grades this. The exams, that's Dr. Morris. Let me see. Delay goes there. And then you don't need a plus. Do we need a plus? No, we don't need one. Okay? So just go up here. Plus, right? Cool. Plus, right? Y of n. Is that correct? And look, here's our puzzle piece. D. Any questions? Want me to do DF2? Yeah, sure, just to get the memory in. Remember these pieces. Remember how I was also talking, let's use another marker because we got to use colors. Remember how I was talking about this right here is our feed forward, right? And this right here is my feed back. Is that a good analogy? What's DF2? Let's flip the 2, right? This is page 4. Okay. So what am I going to do first? X of n, correct? But I have a funny thing where I'm going to put the feedback system right here, and this is my starting signal, right? It's going to start with a plus, okay? Right, plus. And then let me see. Do this right here. You know, I'm going to eyeball things. Remember that piece we had in the beginning? A1, right? And then I'm going to do this right here. Does he do 2 different delays, or does he share the delay in the middle? Okay, perfect. Okay. B1, B0. And then this right here. Let me see. Okay. Let's put a delay here. Cool. Put this there. Don't forget your arrows. Right? And then what happens over here? Plus. And then let's just do a sanity check. This is our feedback, right? And this right here is our feed forward. What is this called? DF2? Were there any questions about that? Not too simple, not too hard. All right, I'm going to throw a curveball at you. Where's A0? Right there, right in the beginning, right? We're assuming that A0 is equal to 1, right? And why did I not make it negative A0? Well, because that's the output we're trying to calculate, correct? This right here sees B0, B1, and this negative term, right? Does that make sense? Well, okay, hear me out. Let me see. It sees that positive 1, okay? So someone's probably screaming at me. You see this 1 right here, right? Okay, just ignore the negatives, right? This output sees plus 1, right? So what am I going to put here? Let me use another color. I don't want to lose you. Let's just use this green. Yeah, this one. I'm going to put a... No, I don't like that one. Let's use magenta. I'm going to put a 1 here, right? Because this 1 is seen by the output, okay? So there's 2 types of engineers, those who put the negative here and those who put the negative right there. In the end, you have negative feedback, so it doesn't blow up, okay? And then what does the output see from here? It sees that delayed x of n minus 1, right? It sees this, sees that. Not too complicated, right? Let's go back over here. The y right here, well, it sees this guy right here, but eventually just sees this right here, right? The 1. Is that making sense? Any questions about that? Anyways, that was 5. And then what I was trying to reiterate is, what if my curveball question was, what if is equal to, maybe you can do this for homework, is not equal to 1. So it's equal to, I'm not saying it's equal to 0, it's or not equal to 0, okay? Not equal to these two. So let's just say, for example, it's equal to, I don't know, A0 is equal to 2. What are you going to do? Divide the system by 2, correct? Or what if it's like 1 divided by 2? You're going to multiply the system by 2, correct? So just make sure, don't forget that A0 term. It's going to be 1. Force this one to 1, okay? Let's see, what's the next part? So have you guys talked about eigenfunctions, right? You're throwing something into the equation itself. Let's show you this. So let's see. How do I want to think about this? Suppose I had a system, and I'm trying to think about it. Give me a second. Let me see. X of, what do you call it, n, is equal to e to the j omega n, right? Right? And then here's my little cute system right here, right? H of k, right? And then I have x of n, y of n, right? Right? Simple. And because we have an impulse response, right? And we have this right here, right? We have an LTI system. That's what he's been like. He's like automatically LTI, linear time invariant. So what is the first thing we do? Convolution. So who remembers convolution? Because I don't remember. I'm playing. I do. So k is equal to infinity.
X of k times h n minus k.
Right? Remember that? H of k, and then what do you call it? X of n minus k. Right? Is that correct?
Yeah.
Which is equal to, if I punch in this x of n right there, right? Infinity to minus infinity of h of k e to the j omega n minus k. Right? Is that familiar? You see this n part right here, right? And then, okay, because some people can't see it. It's okay. I can't see it either. Back when I was an undergrad, h of k e to the j omega n e to the minus j omega k. Now it's making more sense? So what about this term? Does this term care, or does this term influenced by the summation? No. So we can pull that puppy out. Y of n is equal to e to the j omega n, right? And then we have this summation right here. H of k e to the minus j omega k. Does that look familiar to what he was talking about in class? What's this cool term right here? That's the h to the e to the j omega, that frequency response. Which is, by the way, a hint for 2 weeks from now, or no, 3 weeks from now, a lab I'm designing right now for 320. We're going to do some frequency responses. So,
320 what?
320 lab? Yep, we're going to do some frequency responses. It's going to be really cool. Basically, what does the system do, or what do you call it? Frequency response. You throw an input, what comes out? The input again, but with a magnitude and phase, right? What's this right here? What's that equal to? Right? The input, and then magnitude and phase, right? So just replace. So here, I'm trying to show you all. Boom. Okay. So if I were to tell you, page 6. If I were to tell you, okay, I want you to find the frequency response, but you're not supposed to use the cheat tool of the, what's it called, the Z-transform. He hasn't talked about Z-transforms, correct? Good, that's a surprise for later. Don't do it on this exam. If not, you'll be sad. I'll be happy though, but don't do it. Anyways, x of n, right, is equal to e to the j omega n, right? And then I just defined that y of n is equal to e j omega n h e to the j omega, right? Right? Is that making sense? But then this right here is my input, right? Right? So how do I find h e to the j omega? Well, I'm not trying to say divide the whole thing, but we can pop this thing out, but let's just keep it like that. So if I were to give you the following, this equation back here, right? Let's use this purple marker. Y of n is equal to x of n plus x of n minus 1 plus y of n minus 1, correct? And I have this puzzle piece, right? Piece 1 and piece 2, right? Ignore this, okay? Don't worry about that. How do we solve for h, e, j, this frequency response? Just plug and chug, right? Do you want me to use different colors for this one? All right, so I'm gonna use this yellow, okay, for that right there, okay? And I'm gonna use this black right here, okay, for that, okay? Let's take it slow and steady. Y of n, right? How do we gotta replace this with this, right? E to the j omega n, right? H e to the j omega, right? And then let me just, okay, we're gonna have really colorful paper, okay? We have x of n, right? What do we replace that with? E to the j omega n, right? What about this guy right here? It's x n minus 1, right? We got to delay it, correct? Yeah, you guys are getting some value here, huh? E to the j omega n minus 1, correct? Plus. What about this guy? Got to replace it with this, right? Let's put the black marker. E to, and we got a delay there, right? Minus 1. Does that make sense with everybody? E to the j omega n minus 1. And then, what do you call it? H e to the j omega. Why didn't I not put the n in there? Because, well, it's just a frequency response, right? Is that making sense? So now what I do? Combine like terms. Algebra. Let's see if David knows his algebra. So let's just see. If I were to do the following, is anyone bothered if I do this? H e to the j omega, right? E to the j omega n minus e to the j omega n. Oh gosh, I don't want to do that. Okay. Minus 1 is equal to, what do you call it? Let me see. E to the j omega n. Let's not skip steps. Plus e to the j omega n minus 1. Is that cool with everybody? What's the answer that I'm trying to look for? All right? And then let me see. And then, okay, what's the like? Okay, yeah, literally divide them, right? Right? Divide this top term. E to the j omega n plus e to the j omega. Anyone bothered if I'm going to do this? Minus j omega. That's my top part, and then there's my bottom part, e to the j omega n minus e to the j omega n, e to the minus j omega. How do we simplify this? What's the like term in all these terms. E to the j omega, right? That's a like term. This right here, this right there, this right there. So just divide by 1 or multiply by 1 or something like that. E to the okay. Some of you guys are going to take DSP, and this is a funny trick to learn. Multiply by 1, divide by 1 also means this. E to the minus j omega n, right? Divided by e to the minus j omega n. Multiply, divide by 1 or something like that. So then boom, 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 and it gets rid of all that. What's this equal to? 1 minus e to the minus j omega. Woo! That felt good. Any questions? So you guys can do the first question on the exam. Easy, not too hard. Let's see, what else do we have in here? Let's go through this step by step. Because this one might be a little difficult to teach because this is going to take the whole class period on. This one's page 7. Let's see, because I don't want to go too crazy on it. What are the 5 properties? Okay, let's go over this. Okay, so 5 properties. Oh, T's. There we go. There we go. Of systems. Right? Number 1, memoryless. Okay, memoryless. All right. And what does that do? What do you guys remember about memoryless systems?
It only relies on
So we have h of x equal to some constant times the Dirac delta function.
So here's a great answers, everybody. Was I listening? Maybe. So let's just say I'm just going to give you an example. Is there memory in that? No, there's no memory. Good, right? Check mark. No memory. What about this one? Memory, right? Or there's memory, right? There's memory. So it's got memory. It's not memoryless. It's a double negative. I don't know why. Even I thought Dr. Subaru was crazy, so I guess signals and systems people are crazy. Anyways, how about this one? Let me see. How about that one? Has it got memory in it? Yeah? Because if I were to do y of what do you call it? N is equal to 1, right? This is going to equal to x of 2, right? I need to know that future point, right?
Yes.
Or what about y is equal to n minus 1, right? I got to know x of minus 2, right? There's memory. It's relying on something I don't know. If I were walking in time, right, and then there's the Flash, and he sees the future and the past, right? That's not fair. Tell me the answers for tomorrow's exam. He's like, psych. Anyways, this right here, when you see this right here, this kind of thing, it's not memoryless. All right? The exam says maybe. Anyways, any questions about memoryless systems? It's the second property. The causal. I'm going over in terms of what I see. Causal. And what do we remember about causal systems?
It only relies on the present.
Yeah, relies on the present, on the past, right? So here's an example. You see, it's better to give you guys examples. X of, is that causal? Yeah, pretty cool. Give it a check mark, okay? By the way, yes, check marks and X's, or I don't know if he's going to count check marks or X's. Be my guess, or if filled or not filled. Just be prepared to explain what's going on. Can you prove it's memoryless? Right? So if it's not memoryless, can you prove it? Why? Because you can just say, do this. This is a good example. Like prove it, or prove that it is memoryless. Okay? Not too hard. How do you prove that the system is causal? Well, it's just there. Okay, what about this one? Causal? What about this one? X of n plus 1. No, right? Not causal. Okay? Let me give you another tricky one. Because I think we're going to go over time. Let's see. What about this one? Is that causal? Yeah? Because we're only relying on its current input, right? What about this one? Let me see. Let me see how he did it. I don't know if I want to try this one. Let's try it. 0 to x of. Is that causal? So we're just integrating this, right? We're integrating the signal, right? Our input, but it's relying from t, right? The current time. Does that make sense? So we're only caring about our present time. So if this one's like 2 seconds, right? And this right here is 2 seconds, correct? We only care about everything from 0 to 2 seconds. Is that making sense? Now what if I do this? Zero to t plus, what do you call it? I don't know, 1. Because now we're relying on something that happened not at 2 seconds, at 3 seconds. And that hasn't happened. Okay, so this right here is yes, and this right here is no. Okay? Yes, I'm doing it right. Any question? And then same thing for memoryless. Well, if I were to do the following, y of t is equal to, I don't know, x of t. This is memoryless, right? But if memoryless, well, actually, better yet, is this memoryless? We're storing an integral, right? Delays, right? So we need to know a few values, or actually, if this bound right here was, I don't know, minus, I don't know, 10 seconds, right? That's memory. So it's not, this right here is not memoryless. It's got memory. Does that make sense?
Yeah.
So integrals carry memory, and that could be a great thing. Can be a great thing if you're trying to build. It's better to build an integrator than a differentiator, okay? Integrators are pretty nice. You throw it a spike, and it doesn't blow up. For differentiators, you turn off your system, and it goes boom, just like an inductor. You hear that boom?
Oh.
Perfect timing. Anyways, it's page 8. Can't wait to go home, y'all. Anyways, let's see. What about stable? Yeah, what's it call it? BIBO? 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 Same thing? What does bounded input mean? Right? Bounded input? Not too hard. Doesn't go, and it's less than infinity, right? And then what about bounded output? I don't know. I'm just going to call this one A. Right? Not too hard, right? So if I were to give you the following, y of n is equal to, what do you call it? 1/2 n u of n. Is that bounded? Right? Because it just does, it's like this. It just like pulse and it goes boom, 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 right? Bounded input, bounded output. How do you prove it? Well, you just say, hey, you just do the, what do you call it? Absolute sum. And you know this right here, right? You know this right here equals 1, and this will have to go down to 0, correct? Bounded input, bounded output. Let's see. How about this one? No, not bounded input. What happens? Then n goes to infinity. Y of n goes to infinity. Blows up. So this one here is stable. This one here is not stable. Any questions? This right here is page 9. I'm going through all these papers. Oh gosh, hopefully I have enough. Yes, I do. Okay. What's the next property? Yeah, close enough. Or that is right. Yeah, let's go to 4. Time invariant. Okay, time invariant. So what does that mean? So if I do like a shift, if I have my system right here, right, x of n, right, if I shift just the output, right, n minus n naught, right, shift, right, should equal shifted input. Shift inputs. Don't forget the S, okay? So you're going to do this. You're going to shift this right here, the output, right? So you're going to shift this output and see what happens to this. Or when you shift all the inputs, should you get that original equation back? That makes sense with everybody? Any questions about that? Yes?
So, just out of curiosity, because time invariance and variable have an equation that lets you solve it, we have to prove or show our work that it is time invariance or linear, or can we just say that it is?
You got to prove it. So what's that one equation he kept saying? Was it it was like a super thing. Superposition, right? Let me see. Let me remember. Was it throw this signal in? X of 1, what do you call it? I remember shifting. And was it n minus, or what do you call it? Oh, scale it? Oh, that's what, okay. Because I think that's for linearity. That's for linearity. See, that's what I'm trying to go in order. But time invariance is you're doing the shifting output, right? And then you're shifting the input.
So like, would it be like y1 of t is equal to like y1 of t then
Yeah, so basically,
never written down.
let me see. If y of n was equal to x of n plus 1, right? Well, first of all, that's not causal, correct? But if we're going to do this problem, if I were to shift y of n minus n naught, if I'm going to shift the output, right? So I shift all the outputs, or whatever this is right here, right? N minus n naught plus 1, right? Same thing. But if I shift all the inputs, correct? So replace all the n's with n minus n naught. Is that correct? Is that how we do it? So now you just do x of n minus n naught plus 1, right? And it's literally the same thing, right? Okay, this might be a difficult example, but or difficult to understand or see that. But what if I gave you, help me out with this one. This is page 10. Holy molies. You guys are going to get a really good document, huh? What if y of n is equal to x of, let me see, 2n, right? Or not 2n. Let's make it harder. 2n plus 2. Is that correct? So let's shift the output. Let me see. Shift the output. Y of n naught, right? Is that correct? And by shifting the output, I'm just shifting just the n's, correct? So I'm going to get the following. X of 2n minus n naught, right? Is that correct? Plus 2. Okay, that's shifting or doing this. So you're just substituting n's with n minus n naught. Is that correct?
Yeah.
how about if I did, what do you call it? Oh, I remember. It's coming to me. X of n, and you're just shifting all the x of n's by an x of n, x of n minus n naught. Just adding a delay. Add delay, right? Right? So what am I going to do? All the inputs. Just shift the delay, shift the input, right? So this turns into x of 2n plus 2 minus n naught. All right, we have this magic wall right here. Should we show them? Should we compare them? Congratulations, I built a system. Is this equal to? Is that equal? I'm right, right? Huh? Why? It's not time invariant. So this is not time invariant. Are you seeing what's going on? So here's the key tip for today. For this guy, you're going to create two equations. Change all the n's. N's, right? N terms. Okay? But for this one, add delay. Okay? Don't forget that. And then compare the two. Okay? 11. Let's go over the last one, which is linear. Linearity. Is a system linear? Right? And then this is where people were saying, oh, let's just do the, what was it called? The y of n is equal to the alpha x of 1, what was it? T, right? We don't do the shift, it's just scaling, right? So what should I use here? N over, I don't know, A, right? Or was it something else? Right? No? How do we do it? Huh? No, wait, no. We're not shifting it because that's a different property. Sorry, I'm thinking something different. Alpha x1 of n plus beta x of 2. Sorry, because you know why? Sorry, I was thinking two different things. This right here is scaling, right? And this right here is adding. With this guy. That's cool. So how are you going to prove linearity? Just plug and chug these guys into your system, okay? Not too hard. I'm not going to do that one because let me just see if I have any other questions. I don't think I'm going to have time to do this one. Let me see. So I'm going to probably leave that for homework for you guys. Everyone can do convolution, right? So, let me see. 12. Remember that one long problem he was doing was he gave you h of n was equal to, like, I don't know. He gave you something like this. Right? And it was like, I don't know, 1/2, right? Or something like that. And he gives you a train. And then he gives you x of n, right? Let's just say x of n is equal to, I don't know. He gives you the unit pulse right here. U of t minus u of t minus 3, right? And then you're going to have to put the two together. And you have to do that piecewise thing and draw them or something. I don't think, he doesn't ask to draw. I think he just says find the output y of t. And then you're going to just shift and look at them cross together, okay? That one's a little tricky one, but hopefully everyone gets that one, okay? Is that cool? Now the final question is, let's see. Remember the Fourier series and how you can get harmonics? Fourier series. So let's just say I give you impulse response, right? H e to the j omega, right? This right here is your Bode plot. Remember, you're going to, well, if you remember what Bode plots were, if he gives you, I don't know, 1 over 1 minus 1 over, let's say, 2 e to the j omega, right? That's a filter, right? Low pass filter, right? As this goes to infinity, well, this turns into, well, is this a low pass filter? Let me think. Well, this goes to infinity. Well, this term blows up. Yeah, anyways. That's your frequency response, correct? So let's just say I give you an input x of n, which is equal to, I don't know, sine, what do you call it? Pi over 3, right, of n plus cosine pi over, what do you call it, 2 of n. That makes sense? How do I get the, what do you call it, the b's and the k, or the a's? Periodic? Well, is this periodic? Of course, it's assigned. So now that you know it's periodic, well, you got to know there, I think it's called like the resonance, or is it resonances? Well, what we got frequencies in there, right? So we're going to have this pi over 3 term right there, right? You're going to have this other pi over 2, correct? So you're going to have to get their equivalent, what was it called? Fundamental periods. So what's the fundamental period for if I have this condition?
So he's common multiple of pi over 3, pi over 2.
Lowest common multiple. So 3 times 2 is 6. Or is that how it works?
When we find the lowest common multiple, then we just use that to find the fundamental frequency.
Okay.
So the lowest common multiple of 1/3, 1/2 is 1. And then
Or 1. Okay, that's how it goes.
And then we divide 2 pi divided by the.
Okay. Yeah, because I'm not remembering this one either. But point is, you're going to get harmonics out of this guy, okay? So my signals and systems brain, or DSP, thinks to turn these signs into, like, what do you call it, exponentials using Euler's equation. Does he use Euler's equation?
Yeah.
Yeah, literally just sine of, I don't know, was it, I'm just going to write this down because this is how I remember it. What do you call it? E to the j, well, that's omega n. G omega, okay, sine omega n. Is that how we do it? Omega n? E to the j omega n minus e to the minus j omega n, right? All divided by 2j, right? We have a positive frequency, have a negative frequency, right? And then cosine right here, right? Right? Cosine omega n is equal to e to the j omega n. I'm going to put plus, okay? Positive frequency plus e to the minus j omega n all divided by 2, okay? And then that's how you get your harmonic or frequencies, okay? Does that make sense? So can we try to get the Fourier series with this input right here? And I think that's about it. Are there any questions for the exam for tomorrow? All right? It's 1 o'clock tomorrow in that classroom. Good luck and have a good day. I don't think we have a class next week, right? No class next week? No discussion next week? All right. Have a good day.